There's a device sitting outdoors in China right now, about the size of a large dining table, that has been turning seawater into drinking water every single day for over a year. It has no power cord, it's not plugged into anything, no pump, no filter, no electricity bill. It just sits in the sun, and it makes more than 20 liters of fresh water a day. Enough to cover the basic drinking needs of around 10 people. And that water meets World Health Organization drinking standards. That water was also piped into a 5-square-meter test field where it grew spinach, corn, and Chinese cabbage through a full growth cycle. Real vegetables, grown in soil, irrigated entirely by seawater that sunlight turned fresh. The team behind it, from the Institute of Process Engineering at the Chinese Academy of Sciences, working with Shenzhen University, published their results in the journal Advanced Materials on June 21, 2026. And the numbers inside that paper are why material scientists actually stopped and read it twice. Here's why this matters. Right now, 2.1 billion people on this planet still don't have access to safely managed drinking water. That's 1 in 4 human beings alive today. Not treating it, not paying for it, just physically hauling it. And the planet isn't short on water. Oceans hold roughly 97% of all the water on Earth. The problem was never supply. The problem was always cost. For decades, the answer to that cost problem has been reverse osmosis. You force seawater through a membrane with holes small enough to block salt but let water through. And to do that, you need pressure, usually 50 to 80 times normal atmospheric pressure. That's roughly the pressure you'd feel 800 meters underwater, deeper than any human can survive unprotected. On top of that, every liter of drinking water it produces leaves behind roughly 1.5 liters of concentrated salt brine that has to be dumped somewhere, usually back into the ocean, where it can damage marine ecosystems near the outfall. Expensive to build, expensive to run, and messy to clean up after. Solar evaporation always looked like the obvious workaround. Sunlight already evaporates seawater. That's literally how rain happens. So scientists tried building materials that absorb sunlight and turn it into heat right at the water's surface to speed that process up. But every attempt hit the same 2 walls. First, the nanoparticles used to soak up sunlight would clump together in water. Like flour dumped in a bowl without stirring, and once they clumped, performance collapsed. Second, the polymers holding those particles together would degrade under constant ultraviolet exposure, the same way plastic patio furniture goes brittle and cracks after a few summers outside. A device that works great for 3 months and falls apart by month 6 isn't a solution. It's a demonstration. So here's what the Chinese team actually did differently. Instead of solid nanoparticles, they built hollow, multi-layered nanospheres, and then used something called Hansen's solubility parameter theory to precisely thread polyethylene terephthalate polymer chains, the same plastic family as a water bottle, directly through the pores of those hollow shells. Once locked in place, the structure forms what the researchers call a nanoforest. Picture dense, layered undergrowth instead of a flat surface, with open channels running between the layers. Sunlight enters that structure and bounces around inside it instead of reflecting away, which is how the material ends up absorbing 90.2% of the broadband solar spectrum. And because the nanospheres are physically interlocked by those polymer chains, they can't clump. Water moves up through the structure by capillary action, the same effect that pulls water up a paper towel, so there's no pump anywhere in the system. The results are the part that got attention. The material hit an evaporation rate of 38.14 kilograms per square meter per hour, which is 5 times faster than previously reported solar desalination systems. It cut the energy needed to evaporate seawater by 45.7% compared to conventional approaches. To test durability, researchers submerged the material in seawater and stirred it continuously for 30 days. And microscopic analysis afterward found 0 detached particles and no sign of light-driven chemical breakdown. The outdoor prototype, built at 0.75 square meters, has now logged over a year of stable operation with 0 utility energy costs. Now here's the honest part, because this is where a lot of coverage gets carried away. This device produces about 20 liters a day from less than a square meter of surface. That's genuinely impressive for something with no power source, but it's not going to replace a city's water treatment plant. Reverse osmosis was always built for dense coastal cities with grid power and capital. It was never going to reach the roughly 400 million people in sub-Saharan Africa without basic drinking water access, or rural communities without reliable electricity. It's whether it can be built by the ton instead of in a lab, and how fast it gets to the people who've been waiting the longest.
Every single year, the world produces more than 430 million metric tons of plastic. If you loaded all of that onto freight trains, the line would wrap around the entire Earth 7 times. And here's the part that should really bother you. Less than 10% of all the plastic ever made in human history has ever been recycled. The rest is sitting in landfills, floating in oceans, or breaking apart into pieces so small they're now showing up inside human blood, human lungs, and even human arteries. We built the modern world on a material that never goes away, and now it's building up inside of us. But in October 2025, a small team of researchers at a forestry school in northeast China published a paper that made materials engineers stop scrolling and start staring. They said they had created a plastic made from 100% bamboo. Not bamboo mixed with oil. Not bamboo glued together with plastic resin. A real plastic, built entirely from bamboo's own molecules, that runs through the exact same factory machines companies already own, and that completely disappears in plain soil in about 50 days. To understand why this matters, you have to understand why plastic took over everything in the first place. It's cheap. It can be melted and poured into any shape on Earth. It doesn't rust, rot, or shatter. It's the reason your food stays fresh, the reason hospitals can keep instruments sterile, the reason a syringe or an IV bag is safe to use. Getting rid of plastic sounds simple until you realize you'd be ripping out one of the load-bearing pieces of modern life. But the same property that makes plastic so useful is exactly what makes it so dangerous. It doesn't break down. For decades, scientists have tried to fix this, and almost every attempt has failed in the exact same way. Take PLA, the most common bioplastic, made from fermented corn starch. It only breaks down inside special industrial facilities held above 58 degrees Celsius for weeks. It's also weak, it can't handle heat, and it eats up farmland that could be growing food instead. Then there's FAR, which breaks down more easily but costs several times more than regular plastic to produce. So it's been stuck in tiny niche products for years. Starch-based plastics dissolve the second they get wet. Cellulose acetate is stronger, but making it requires harsh chemicals that defeat the entire point of going green. For 50 years, the plastics industry has been stuck picking 2 out of 3: strong, biodegradable, or affordable. Nobody could get all 3 at once. That wall is exactly what a team led by researchers Xingyu Wu and Daowei Zhao at Northeast Forestry University in Harbin, working with Shenyang University of Chemical Technology, just broke through. Here's why bamboo was considered basically impossible to work with before this. The cellulose inside bamboo is locked together by an incredibly dense web of hydrogen bonds, which is what lets a bamboo stalk stand tall in strong wind, but those same bonds make it almost impossible to reshape. Try to force raw bamboo into a mold and it just snaps. Earlier attempts at bamboo plastic cheated around this by grinding up bamboo fiber and gluing it together with regular plastic resin. It looked green on the label, but it was still half oil, and it still didn't biodegrade. What this new team did was completely different. Instead of mixing bamboo with plastic, they turned bamboo into plastic. First, they soaked bamboo cellulose in a solvent made from zinc chloride and formic acid, which unlocks those rigid hydrogen bonds without damaging the molecules themselves, like carefully untangling a fishing net instead of cutting it apart. Then they added ethanol, which guides the freed molecules to reconnect into a brand new structure, tighter and stronger than the one bamboo started with. The result is a material built from 100% of bamboo's own molecules, no synthetic glue, no petroleum, nothing left behind. They named it BM plastic, short for bamboo molecular plastic. And the test numbers are what actually silence the skeptics. BM plastic hits a tensile strength of 110 megapascals, nearly double PLA, and stronger than high-impact polystyrene. It scored 6.41 gigapascals on bending resistance, beating ABS, the tough plastic used in car dashboards and Lego bricks. It holds its shape above 180 degrees Celsius, survived 7 straight days at 100 degrees Celsius without cracking. Then, in plain soil with no special facility, it was essentially gone in 50 days. The full dataset was published openly in Nature Communications, so any scientist on Earth can check the work. Bamboo isn't a random choice either. Some species grow more than 1 meter in a single day. A harvested bamboo forest fully regrows in 3 to 5 years compared to 25 to 30 years for pine, with no replanting needed. China alone has more than 7.5 million hectares of bamboo forest across roughly 20 provinces, an industry already worth close to 320 billion yuan, supporting over 7.5 million farmers. And it's already happening. China launched a national plan in 2022 to substitute bamboo for plastic, followed by a formal 3-year action plan in 2023. It costs around $2,300 per ton to produce right now, compared to roughly $12,000 to $2,200 for regular plastic, and researchers say that gap should shrink fast as production scales.